related to YT. So I thought it might be more interesting for you for folks here. So what it is a package that has been developed over a long time called Caesar, which basically is a Galaxy and Halo catalog generation and management software. Okay. And now it's kind of focused on galaxies and halos, but you can really think of this much more generally than this. You have small lumps within a big thing, right? And if you have a bunch of big things with little small lumps, could be like molecular, protostars within molecular clouds or whatever, right? This is a framework for handling those kind of objects and data sets. So it was originally written by Robert Thompson, started when he was my postdoc in South Africa. He then went to work with Matt, and Matt said, no, you must be YT compatible. And so that's what Robert did.
I was young.
And so it's now all sort of effectively a YT extension package, which has been great, of course. But Robert left the field, so now it's kind of in as much as being made. Well, actually, I worked a lot on it to rewrite the backend and stuff. It's myself and Daeshik. Okay, so what is Caesar? Again, it's this Galaxy catalog generation software. So what does it take as an input? Okay, so you give it a snapshot, and again, YT provides a great front end for this, right? You can read in all these different formats. We've analyzed Simba, Eagle, TNG snapshots using this, right? You can also give it a list of Halo IDs, right? You can use YT's friends of friends if you don't care that or just want to use something, but it also accepts other Halo things, or you can read it from the snapshot, right? So if you have a Halo finder that you do on the fly, like we do in our simulations, and that provides a list of particle IDs that are in halos, you could just take that from the snapshot. So there's many ways to sort of put in your halos. And those are kind of the units that we work with. We work halo by halo, right? So what does it do, given all this list of halos? So it identifies bound lumps. So it goes through and runs a 60 friends of friends, right? So that's the idea. And you can assign some criteria for what you want to put in these bound lumps. For instance, in the case of our galaxies, we want cold gas that is dense, right? So we have a temperature and a density criterion that says, go look at all those particles. From there, do a 60 friends of friends, and you can tell it your favorite linking length. And I mean, it has everything built in if you just don't want to care about that, but you can provide like linking lengths in both spatial and velocity. Okay, so then it goes through and creates this cross-matched big catalog between galaxies and halos. For each galaxy or halo, it computes a huge number of physical properties, which I'll describe. Can even do things like identify progenitors and descendants of those things and other snapshots. And then it outputs a single catalog file per snapshot. So for each snapshot, then you have your associated Caesar catalog. So what's in this thing? Obviously things like masses. So you have, but all these various components, right? So you can have, stellar gas, black hole, etc. Obviously positions and velocities, center of mass, or the minimum potential thing, which can be useful, particularly for like clusters or whatever. Various radii, various metallicities, all these things are all pre-computed for you for each object, both galaxies and halos. Velocity dispersions, rotations are interesting. It computes Euler angles. So if you want to rotate your galaxy so that it's face on or edge on, you can do that, and Caesar has some functionality that allows you to do that. Computes, bulge to total, etc., in various ways, and then of course, various other things. Also has some CGM temperature properties as well, right? Where CGM is defined that anything within the halo that's not identified in a galaxy is the CGM, right? Local environment, etc. And then there's extra things for halos, things like virial masses and virial radii out to various commonly used overdensities, spin parameter, etc. So you have this big catalog that contains all this information, right? That you can just use very easily. Also does photometry, just for the heck of it. Okay, so we want to do, you want to know, whatever the Euclid bands photometry for all your galaxies, right? It just goes and does that for you, and it So you can use various SPS models, right? It's all based on FSPS. It's kind of the front end, but you can input other population synthesis models if you like. So, so the first time you go through this, so we provide on the website some on the on the GitHub some basic packages for I think for all of those three, but you might want a different IMF, right? Like for FSPS's thing, we have Chabrier IMF and with emission lines. But if you don't like that, you can run your own model through Caesar. So you just provide the options. It will generate a catalog for you, right? Once it generates the catalog, right, in the command, I'll show you how that's run, you can read it back in. So it goes, looks for that command, looks for that catalog first. If it's there, reads it in. If not, it'll create it so the next time you have it, and it'll be much faster. Once it does that, it's very fast. Okay. The other cool thing it does is it does dust extinction. Okay. So if you have either a field of dust or a metallicity field, right, which you can specify how to convert it to dust. Actually, that's hard coded, which I shouldn't do. But anyway, so basically what it does to each star particle, it says you pick a direction, you say, what's the total column density of dust along that line of sight, right? And it's done with, sorry, I didn't use rays here because I really wanted to get the proper kernel integral through the SPH kernel, which means it's kind of maybe doesn't really work with AMR yet. We should probably just use the rays for that. So that's probably something should be added. But anyway, but in principle, like the rest of it would be very easy. We just need to use the raise command for that instead of that. But otherwise, it does that, computes, then you can get an AV for a galaxy, for instance, and it takes anything that's extincted, just does an energy budget and puts it all into the far infrared luminosity, and that's also an output. Obviously, it doesn't do the full radiative transfer to get the far infrared SED and all that, but if you just want a quick number, right, that's the number. Various choice of extinction laws, both absolute and apparent magnitudes at any redshift, and gives you both dust and without dust. So you can actually get it to output the full bit galaxy spectrum. It's not super easy and it's not documented, but it is possible. So that functionality is in there. Many things left to be done. Okay, so how do you actually generate one of these things? Okay, so you go download Caesar, of course. Then, usual thing, you import YT, import Caesar, load your YT snapshot, then you create a Caesar object. Okay, so then you have a Caesar object called, in this case, OBJ. Then what you do is you run this particular code called member search. So this does the catalog generation. And again, you can see it's specifying a huge number of options here. There are many more, but here I'm telling it to run the friends of friends on this. If I said like snap, it would be, read it from the snapshot, whatever. Then it goes through and identifies halos, if you're telling it to, right? And again, it's the same deal, right? This file, it will look for this file if it's there. If not, it will generate it. So the next time through, you don't have to redo the friends of friends, right? Same thing with the 6D friends of friends to identify the galaxies within the halos, right? Same deal. You can specify this file, try to read from it first. Then there's a whole bunch of things for the photometry. Here's your SSB, your table file for your population synthesis model, etc. And right, nproc equals 8. So it is actually at least OpenMP parallel type thing, right? And this was like an entire summer of mine was learning how to do Cython parallel and making that like much faster. So unfortunately, it's still a bit of a memory hog. So this is the main issue with this code at the moment. I'll mention right at the end. So then, of course, you have to save the file. Okay, so then what do you do with it? So the basic structure of the catalog file, if you just do an H5LS, you'll see galaxy data, global lists or particle lists. You can't really access that or not easily. Halo data, simulation attributes. So these are all header information. A lot of it is copied from YT, but if you don't want to, you just have it within Caesar, and then some progenitor data as well. So then there's a bunch within each of these, let's say galaxy data, there's a bunch of top level quantities, but then most of the quantities are actually stored in these dictionaries. And the reason we store them in dictionaries is so that we can have nice names. Right? Like you can say, give me masses black hole, right? So this gives me all the black hole masses of all the, well, whatever object I'm doing, galaxies, halos, or half-mass stellar radii or something like that. So any of the Dixon quantities can be accessed this way. So just to give you some examples, right? So, what we do with like, our Simba simulations, whatever, we pre-generate all these catalogs and just put them on the website, right? So then you can just use them, right? And you don't need to import YT or anything. You can just basically use the catalog, right? So then you just directly load your Caesar catalog. Then again, there's this thing called dot simulation. So I'm creating I'm loading in this catalog as sim. Then sim.simulation has all these header information, for instance, redshift, something like that. Much more, of course. Then you can treat it within sim. Now we have these sort of objects, these galaxies and halos, right? And they are really like Python objects, right? So you can do list comprehension, for instance, right? So you say, give me all the galaxies with stellar masses greater than 10 to the 10. Right, so now you have an array of galaxy objects which satisfy this criterion, right? Then I can say, okay, give me the masses, stellar masses for these objects. Okay, so now I have an array for that. Then here's star formation rate, and what I want to show you here is the unit conversion, right? So it works just like YT. We have the unit conversions, right? So we can, generally the stellar masses are in solar masses and the star formation rate is solar mass per year. But if, for good practice, I always include the unit conversion anyway. And then, so that works just like that. And then here's the real fun part, right? The galaxies and halos are cross matched, which means that if I want the halos for these galaxies, that's really easy. The halo objects are just the galaxy dot halo. So every galaxy knows which halo it belongs to, right? So this basically is now telling me, give me all the halos for all these galaxies if the galaxy is a central, right? Because we track whether a galaxy is a central or satellite. So all these halos are cross-matched. So then now you can, again, get the halo masses for those, right? In that case, the total overall halo mass, et cetera. Be aware these things are lists. They're not NumPy arrays. So if you want to, work with them, you have to just convert them. Okay, here's another fun thing. Suppose you look through your 300 properties or whatever, goes, they all suck. I want to do my own. Okay, fine, easy. Okay. Caesar also contains the particle IDs for each galaxy and halo, right? So it means that you can go back to the snapshot. Okay, now you're going to need the snapshot. Go back to the snapshot, look up those IDs, say, for my galaxy, for whatever galaxy, I can compute my own properties from whatever part, whatever I want. Okay, so you don't have to use the Caesar properties if you don't want to. So these are in these things called G-list, S-list, black hole list, self-explanatory, EM list. Same for halos. So you do need to do something to load in the raw particle information. So we have this tool, PyGadget Reader, which is just a wrapper for reading HDF5 files from a variety of things. So like this is how you would compute. This is not a quantity we can pre-compute, the star formation rate weighted oxygen abundance. But like once you put in the metallicities, once you read in the oxygen abundance for each particle and the star formation rate for each particle in your snapshot, you can go through and basically say, give me all the star formation rates in this particular galaxy for each of my galaxies here, right? So it loops over all the galaxies, collects all the star formation rates, collects all the oxygen abundances, do that little, weighting that we all like, and voila, Z-oxy now contains the oxygen weighted X-ray star formation rate with oxygen abundances. So that's how you can work with the particle list. Very easy. All these examples are on the read the docs page. So there's a lot more, but I think in the interest of time, we'll stop. But yeah, I think it's really it's been super helpful for us because it's like it allows, like, for instance, students and everything to get up to speed really quickly. just a few Python commands, and you can read in data sets, make plots, go to town, and it's all compatible with YT. So you can read in, we use it, for instance, to read in halo particle lists, and then we can, make YT plots just based on those halo particle lists or just based on the galaxies within the halos, et cetera. Right? So you don't have to use arbitrary cuts for whatever, right? CGM definitions, right? You can actually see what's in the galaxy. Yeah, and it works with, as I said, it's not, okay, look, it's not as well maintained as something like YT. I'll just put it out there. but so your mileage may vary, but it does do a lot. And we're always open to pull requests. So if you have something that you'd like to see, and we can help you work to put it in. So yeah, that's about it. As I said, it does a lot more. And then the one thing we're working on now in our copious spare time is the successor to Caesar, which is called Octavian, of course. And the main improvement of that is we're removing all the Cython parallel crap, because that was my pet project and I was pretty stupid about it, and replacing it all with pandas, which turns out, well, there's just a huge amount of index manipulation. Pandas is really the right way to do it, which my student, who's a much better Python developer than me, my undergrad student, knew. So he actually rewrote all of it, all of this stuff into, it works, but it has none of the bells and whistles. And now he's starting a PhD somewhere else. So on another topic. So, but the key thing is it'll be MPI parallel, right? And that's really the key thing, because that will allow us to scale up to now whatever simulation size without being memory limited. So yeah, anybody is interested in helping us out with that, we would love to have help. Okay, that's about it. Thanks.
You're on Romeel. Does anyone have any questions about this? I don't have a question, but I'd love to get this working with Enzo.
It should work with Enzo.
The way.
I think Bobby, when he was there, made sure it worked with Enzo. I mean, the Caesar doesn't care what your particles are, whether there's particles or cells, except for the photometry, the one issue. Other than that, it shouldn't care.
Right. I'd also like to.
You'd have to figure out some way to identify the cells to be within a given halo or galaxy or whatever, but that could be.
My feeling is that the YT's MPI helpers be quite useful for MPI parallelization.
Okay.
Methods of doing that.
Okay. Nice.
I'd be happy to talk more about that. Quite interested.
Trying to make it work with Enzo and Ramses.
And
Ramses.
yeah.
Yeah, I mean, we have so I've never used it with that, but it has whatever the translation tables for Enzo and Ramses in Caesar. So somebody must have tried it once. But yeah, your mileage may vary. Yeah.
Fantastic. Thank you. Oh, that's great. None of these historical. All right, next up is me. Number TD season.